Okay, so with sample problem D, we're actually going to pick up a little bit where we left off. And yes, I know that what you have in your notes looks slightly different than what you see up on the board. Okay, the one up on the board has a little bit more of a grid, and that's okay. It just kind of help us with certain things, although I think what you have in your notes will certainly be fine. Okay? Let's rewind a little bit to last unit. In our energy approach, we were able to take graphs of force over displacement, or position, to figure out an amount of work being done. The nice thing about it is, we were able to do that for situations where we had what we call in physics land non-constant forces. Okay? Where we couldn't just do F equals ma with a non-constant force. Okay? We have the same principle that applies here, except now it's not a force versus position graph, it's simply a force versus time graph. Okay, so we can dissect situations that are non-constant force situations to find and determine what the impulse is going to be for a certain duration of time. So what I'm going to ask that you do is to go ahead and take but a couple seconds, and let's find the impulse for the 3 durations of time here in sample problem D. Go. All right, so here we go. Let's check in on what we have. Okay, some of which has been highlighted here. We'll kind of get to that highlighter in just a second. Put that in blue. Okay, so for part A, okay, in part A we just have the right triangle that is highlighted in green. Okay, certainly, question came up, Jason. Okay, what do we do to show work for this, just to make sure that we're all good with it? Okay, just show me something. Whether you're labeling individual parts, because let's be real, for that one, just the area of a right triangle, 1/2 base times height. Okay, so we can just go ahead and do that. Or you can go ahead and show 1/2 base times height. Substitution. Okay, having your support for that.
Pardon the interruption.
Okay, so 1/2 base times height. Find the area of our right triangle. Find out 50 Newton seconds. We all agree 50 Newton seconds? Yeah. Yes, we should. Okay, that's what it is. Okay, part B, we just have the rectangle that is right next to that. Okay, length times width. Should be pretty easy. 100 Newton seconds. Then we need to do the last bit. Now you can do it 2 ways, which is kind of highlighted on the board. You can break it up to the right triangle up top plus the rectangle that is down below. Or if you happen to know the area of a trapezoid equation, which is actually really just a combination of the right triangle equation and the rectangle equation, that we would go ahead and find it that way either. But can we find that to be, what is that, 144 plus what we already had, okay, to find the total as we were asked in part C for 294 Newton seconds. Is that what everybody gets? Good. Okay. So just understand that with impulse, okay, if we have the graph that is a force versus time graph, okay, no matter what the force values are, we can still figure out what that impulse is going to be. Good. Period. Space. Start of a new paragraph. Okay. Let's start talking about collisions. Okay, because what we had previously was more of a continuation of what we had from last class. Okay, today, collisions. A collision, how I'm going to define it, is simply going to be a momentum interaction between 2 or more objects. We're typically going to focus on 2 objects here, but it certainly could be more than that depending on what the scenario dictates. More specifically than that, there are 2 types of collisions of which we will take a look at. Elastic collisions and inelastic collisions. By textbook definition, an elastic collision is a collision in which the total kinetic energy of the system is the same before and after the collision. Okay. What we typically see as elastic collisions are scenarios where 2 objects collide and they rebound off of each other, having their own unique final velocities. Okay. Sometimes a common example of this is if you're playing pool, you have the cue ball and one other ball, and the interaction between those 2, typically, okay, once you strike the cue ball as it rolls into the next one, okay, they have 2 independent final velocities after they collide with each other. Okay? You'll see that we have the equation that's down here below. It looks like a lot of numbers and subscripts, but just understand all it really is, we have 2 objects, and their initial momentum. So m1v1 initial is the initial momentum of one object plus the initial momentum of another object is going to be equal to the sum of the final momentums of those two objects. Okay? And that's all we really have in an elastic collision. Oh, wrong way. And in elastic collision, okay, is defined as one in which the total kinetic energy of the system after the collision is not the same as it is before. Okay? What we will find is a very specific type of inelastic collision that we will talk about in the context of this class in our very quick momentum and collision unit. And that is, when they stick together, we call that a complete inelastic or sometimes a total inelastic collision. Know that in a total inelastic collision, there is the greatest amount of kinetic energy lost as part of that collision. Now, understand that in a lot of these collisions, there actually is an energy loss that is not necessarily attributed to friction. Okay? In our energy unit, I think that was kind of the go-to for some of us to describe energy loss. Well, it was friction, and friction affects it this way. Okay? You see two images at the bottom of this slide. And the one on the left is a golf ball being hit by a driver right at the moment of impact. What do you notice about the left-hand side of that golf ball? Okay. Certainly flattened as a result of the impact force imparted during the duration that it's in contact with the driver itself. We did a problem in our last unit. Now, that actually, there's an incredible amount of force that's applied to that golf ball. And I think most of you would agree, no one in this room can take a golf ball between their fingers and cause it to flatten in the same way that it does there. Okay? A golf ball is a very rigid object. But in that moment of impact, even a golf ball, it is going to deform. Its physical shape is going to deform as a result of the force that's imparted on it during that time. Now, golf ball is hit by the club, starts to travel through the air. Does the golf ball stay as that shape after the collision? No. So what does the golf ball have to do directly after that collision? It has to reform its shape. Okay? And it is going to spend some of the energy it was given to reform the shape that it initially had. Okay? And one that's kind of a little bit more of an example of that, the image on the right, okay, you see a racquetball. Now, everybody in this room could deform a racquetball. Okay? It does have a little bit of squishiness to it, okay, a little bit of flexibility to that, okay, whereas the moment of impact, certainly it is going to deform a great amount. Okay? But in the same way, post-collision, okay, it is going to have to spend some of the energy it was given to reform itself. Now, kind of rewinding a little bit back to the concept of a total inelastic collision, okay, that specific collision is one in which the objects kind of couple together post-collision. They travel together after that impact. What you will notice is this equation is actually almost exactly the same as the previous equation. There's only one difference to it. What is it? There's just one V final because they travel together. Okay? So if you want to think of it this way, we've kind of undistributed the V final from both of those terms. Okay? Because it is the same quantity. Okay? Now, one of the things that we will have to do, and it's not always told to us in the problems, you may need to figure out what type of collision are we dealing with. Okay? Because not every problem is going to explicitly state. This is an elastic collision. So this is a total inelastic collision. Very simple to tell. Typically, if you are given one final velocity and asked to solve for the other, what does it have to be? It has to be elastic. Okay? If we're just told in some way, shape, or form we can see in that scenario, those objects are going to couple together and travel together post-collision, it has to be total inelastic collision. Okay, when we go ahead and we only have that one final velocity. Okay, our best way to kind of understand what it is that we have to do is just go ahead and jump on in. So we're going to do 3 relatively quick sample problems, and be good to go. Okay, so a 7 kilogram bowling ball rolls into a 2.27 kilogram pin in an elastic collision. So in this problem, we're actually told the information that we need. Okay, the bowling ball hit the pin with an initial velocity of 8.3 meters per second. If the final velocity of the bowling pin is 7.2, what's the final velocity of the pin? Lots of wordiness to there, but we have some things to follow. So, let's do this, okay? Let's rewind to the elastic collision equation. Let's kind of talk our way through this so that we can get the rearranged version. First off, bowling ball, bowling pin. Does it really matter which one we call mass 1 and which one we call mass 2? No. But what does matter is the correct association of data, making sure the correct mass is associated with the correct velocity. Okay, because if we start mixing that stuff up, we're going to have some difficulties with it. So, in this problem, we're asked to solve for the final velocity of the pin. So if it's okay with you, I would like to make V2 final the bowling pin. The last term here just makes it easier to rearrange, which would mean bowling pin is mass 2, velocity 2, all of that information. Anything with a 2 designation, bowling pin, making all the designations of 1 are bowling ball. What do we need to do to M1 V1 final? If we're trying to solve for V2 final, subtract that from both sides, which would be M1 V1 initial plus M2 V2 initial minus M1 V1 final, and then divide by M2. Okay, so let's go ahead and let's write that out here. Okay, so that would be, let's get the pen. V2 final would be equal to, okay, I'm going to kind of block this out a little bit differently with parentheses just so we can kind of see, because there are going to be a bunch of parentheses I would like for you to use. M1 V1 initial plus M2 V2 initial minus M1 V1 final, closed, close, and then all of that divided by M2. Okay, friendly reminder, since we're finding the velocity of the pin, that is 2. I'm going to just mark it here. The pin we're calling object 2, the bowling ball we're calling object 1. So let's go through our substitution. Okay, open, open. Mass 1 is our 7 kilogram bowling ball times its initial velocity, which is what? What is a 7 kilogram bowling ball? What's its initial velocity? Good, 8.3. Close it off. Plus, open parenthesis, mass 2, which is 2.27, times its initial velocity. Now, I don't know about you, but the times that I have gone bowling, the pins have an initial velocity of 0. Okay? They are not moving at the time in which I am starting to roll the bowling ball down the alley. Minus M1, which is 7, times its final velocity, okay, which was the other remaining velocity, which is 7.2. Okay, close that off. All then divided by mass 2, which was 2.27. Pluggy chuggy. Let's figure out what V2 final would be. And while we're plugging that in, yes, please plug it in as one big long string. Okay? While we're doing that, remember that we should be getting a reasonable value for this. Okay, our bowling ball had a velocity of 8.3 that was reduced to 7.2 meters per second. We should expect that our stationary bowling pin is certainly going to increase its velocity, and at least based on this initial collision, should probably be a positive value because it's going to go in the direction that the bowling ball was traveling. Mark, when you feel like you got it, let me know.
I got 3.392
meters per second. How many of you by show of hands would agree with that as a response? Okay, we should. Okay, Very reasonable value considering our scenario. Now, if you were not told in this problem that it was an elastic collision, how would we know? We're given a final velocity and has to solve for the other. So I think that piece of it probably rather direct. All right, sample problem F. Okay. A Smart 4.2, 730 kilogram Smart 4.2 is sitting at a stoplight. A 5,919 kilogram Ford F450 makes a total inelastic collision with a smart car at a speed of 20 meters per second. Clearly, we've chosen two vehicles on opposite ends of the mass spectrum, just so we can kind of see the net effect of all of this. Now, we are told that this is a total inelastic collision. So real quick, we're going to take a rewind back to our inelastic collision equation, total inelastic collision equation. If we're going to solve for V final, this one's pretty easy. What's the only thing we really need to do to rearrange for VF? Divide by M1 plus M2, okay, the sum of those masses, okay? So let's go ahead and write it out as such, okay? V final equals M1 V1 initial plus M2 V2 initial, all divided by M1 plus M2, okay? Why don't you go ahead and carry out the rest of this problem from start to finish. In the same way, does it matter what we consider mass 1 and mass 2 to be? Not really, so long as we are consistent with our data association. And the correct velocity is associated with the correct masses. Roman, what do we get?
17.04 meters per second.
Okay, 17.084. Oh, sorry. You said it right. I goofed. Let's correct that. 17.804. Okay. Meters per second. Okay. Let's think about this for a second, or for a second. Okay. Does that make sense? I would say, considering the situation, yes. But what I would consider to be equally as important, let's consider that from both perspectives. If you are in the F450 as the driver, I don't know why we're getting the collision, but we just do. Okay, you start off with a velocity of 20 meters per second, which is a little more than 40 miles an hour. Okay, and your velocity is reduced to 17.8 meters per second. About a 5 mile an hour drop, so almost like you just kind of hit a speed bump, I guess. Okay, but if you are in the smart car that is stationary, you go from a velocity of 0 to 17.8 meters per second. That's a rather significant velocity change as a result of that collision. Now, just for kicks and giggles, in part B, I want to do the exact same problem, but switch the vehicle. Okay? Now let's go ahead and let's take the F450, have it stationary at the stoplight, when it is our Smart 4.2 that's traveling at 20 meters per second. Okay? If you haven't done so already, let's go ahead, let's solve part B. Will got a quality response? What'd you get? 2.196 meters per second. Okay? Is what we get for that. And again, let's consider that from both perspectives. Okay? If you're in the F450 sitting in a stoplight, Smart for 2 collides with you in the total inelastic collision, final velocity post-collision, at least right at the moment of impact, 2.2 meters per second. Like a little pleasant thought. Okay? However, if you are in the Smart car going at 20 meters per second, your velocity gets reduced to 2.2 meters per second as a result of that collision. I again would consider that to be relatively significant. Now, let's answer part C before I have another talking point for us. Why are those two velocities, the velocity for A and the velocity for B, so different? They're the same vehicles. Why are they so different? Let's answer it. Okay? Well, obviously mass. Think about the momentum. This is a momentum unit. Okay? That each of them carry into the collision. Does a Smart car carry a whole lot of momentum for a passenger vehicle into the collision? No. And then all of that gets distributed between the two since they couple together as a result of the collision. It's not carrying a whole lot of momentum into the collision, so therefore post-collision, it is going to have a greatly reduced velocity. Whereas the F450 carries a lot more momentum into the collision itself. Okay, so the combined masses of the two of them are certainly going to travel at a much higher rate of speed. Now, does this mean that everybody should be driving F450s? No, actually quite the opposite of that. Those vehicles, typically, like I'm talking like that real heavy duty pickups, not even like the light duty pickups or the other ones. But those vehicles carry so much momentum into these collisions that often they have a hard time dissipating the energy that they carry into those collisions. Okay? They have a harder time dealing with the amount of momentum that they bring into the collision itself. So the answer is not either of them. Everybody should not be driving F450s or Smart cars because they have their limitations with that. But just something to consider that certainly these bigger vehicles, they are going to carry a lot more momentum into the collision. Okay, questions on anything here? All right, our last sample problem for today. Some of you may question when you read it and say, but Talbot, this isn't really a collision. Sure, kind of. The way I'll define a collision, as some have a tendency to do, is that it is a momentum interaction between two or more objects. And a cannonball being fired from a cannon, the way in which we're going to dissect it, is a momentum interaction between two objects. Okay? Now, we could treat this as most people in physics land would do. They would treat this as a law of conservation of momentum problem. Okay? I have the tendency to dissect it a little bit differently than most might. I'd like to show you that and just kind of, because I think it's the easiest way to deal with it. Okay? We're going to treat this as a collision. What type of collision would it be? We are given a final velocity and asked to solve for the other. Okay? It would be an elastic collision. Okay? However, what is the initial velocity for both objects pre-collision? 0. So think about the elastic collision equation. M1 V1 initial plus M2 V2 initial. All of that is just a big goose egg. Equal to M1 V1 final plus M2 V2 final. So what if we brought the M1 V1 final to the left side of the equation, because it was on the right and all of that was set equal to 0, and set that equal to M2 V2 final. Everybody see what we did here? We're using the elastic collision equation, but since both the cannonball and the cannon have an initial velocity of 0, that whole left-hand side of the equation becomes 0. So then all we're doing is we're basing this off the final velocity that they would have projecting in opposite direction. And I hope everybody understands when the cannonball is fired one direction, there is a recoil velocity of the cannon going back the other direction. That's what it is that we're trying to find. So, if we're trying to find the recoil velocity of the cannon, and kind of using the image of what we have here, let's designate the cannon as object 2. Because that way all we'd have to do is just define V2 final in this equation. What would we do to isolate V2 final? We divide both sides by M2. So let's kind of do the rearranging all at once. V2 final would be equal to negative M1 V1 final, all divided by M2. All right, so here we go. Open parenthesis, negative, what is mass 1? Our cannonball's mass is 4.2, okay? Times, what is its final velocity? Negative 470. The negative is certainly of significance. All divided by the mass of our cannon, which we're told is 453 kilograms. Let's go ahead and solve for V2 final. Couple things to check with this one. One, we are expecting this to be a positive value because as our cannonball is projected to the left, our recoil should be to the right. And it should be a reasonable rate. We were able to share a nice chuckle in last class because the person we called on gave the cannon a final velocity of 1,600 something meters per second. And again, that's because of parentheses is the way it worked out. But I hope that we understand that the cannon should not be traveling more than a mile per second as the recoil velocity once it fires a cannonball. We would have issues if that would be the case. So make sure it's a reasonable quantity for what we get. Okay? And Sebastian, what do we have for V2 final? Okay, we'll give you a second. Take your time. Anything but 1 mile per second will be an improvement over what we had as our initial response in last class. So I hope that we are not in the range of 1,600 something meters per second. 4.358 meters per second is Sebastian's response. Show of hands, how many agree? That help out? Okay. And again, does that make sense? Okay. Positive velocity. Are we expecting a positive velocity for the recoil in this case? Yeah, absolutely. Okay. Is that a reasonable recoil velocity considering the situation? The object that has much more mass is not going to have as great a velocity after the momentum interaction between these two objects. Okay, that's all we have for this. Okay, any questions at all on all three samples?